Hi, I'm Jack Heslin, founder of the AI Conversation, an online community where people and organizations of all different backgrounds come together to learn about and share how to use AI tools. The goal is to create a best practices forum so we all learn how to use in the best way possible these extraordinary tools. So, welcome back to our continuing series AI 101. Our goal in this series has been to give people basic concepts of what we've called the AI pyramid and about how one layer builds on top of the next. Now, here we're getting pretty near the top of the pyramid. This is our module on computer vision. Computer vision, this is a remarkable technology that gives AI systems the ability to, well, see the world around them really. Um, to really respond to the world just like eagles do. Eagles are going to be our metaphor. You know, we had Clydesdales for machine learning, we had octopuses for deep learning, we had the beaver for expert systems, and then in the last module we used the parrot for natural language processing. Well, just like eagles have really incredible vision that allows them to spot the tiniest of details from far away and high above, computer vision systems can analyze and interpret visual information with extraordinary precision. So in this module, we're going to talk about how machines, and that's what computers are, machines process images and videos to detect patterns, recognize objects, make decisions based on what they see, and then react to it. So obviously this is a huge part of self-driving vehicles, but today it's also in medical diagnostics and other applications, which we're going to get to in a couple minutes. But the thing that, even though there are challenges with computer vision, and we're going to see those in a little bit, this technology, like all AI technologies, is absolutely is absolutely going to transform all manner of industry, profit, nonprofit, government. It's going to become quite pervasive. We're not saying that's a good thing. We're not saying it's a bad thing, but it is certainly something that's going to be happening. Now, why the eagle? Why the eagle? So we're climbing our AI pyramid. We've gotten pretty high on it now. We're one level from the top. So why did we choose the eagle for this particular metaphor? Excuse me, this particular technology. Well, eagles have the most extraordinary vision that allows them to spot the tiniest of prey from amazing distances while they're circling high above. And they can process that visual information instantly, make split second decisions. And then similarly, computer vision, it's kind of designed to be just as sharp eyed and detect patterns in the way that the eagle does. And analyze images quickly, identify those objects, the relationship those objects have to their surrounding environment. You know, if you're an eagle, you want to know the rat from the underbrush that it's scurrying through. Um, so to determine those relationships in of the items that are the objects that are in the field of vision, computer vision sits at the second to top layer of our AI pyramid. Now the layers we've explored: machine learning, neural networks, expert systems, natural language processing, all support computer vision. And now computer vision is the supporting block for AI robotics, which will be in our next module. But the eagle perfectly captures this particular, we'll call it an AI superpower. Have a little bit of fun here. But what it's really doing is it's giving the machine the quote superpower to enhance one of our most primary senses. So what exactly is computer vision? At its core, it's a branch of AI. That's why it's on our AI pyramid. And it's a branch of AI that enables machines to interpret and make decisions based on visual data like images and videos, basically giving computers the ability to see just like we do. Now, this powerful field sits at the intersection of computer science, AI, and visual processing, which allows systems to perceive their environment much like we do, very much the way human beings do. Computer vision has come a long way over the decades. This isn't a new concept, But there was a time early on in this technology when a computer would struggle to tell you, what's a square and what's a circle. And it's come a long way since then. So from simple image processing that could barely detect basic shapes, today these sophisticated systems, and they are sophisticated, can understand complex scenes, recognize thousands of objects. This evolution has been driven by advances in algorithms, computing power, massive amounts of visual data now available. And that's so interesting to think about. Smartphones have cameras. They've had cameras for years. Even before they were smartphones, cameras were on phones. So we record the visual world um, in greater quantity than we've ever done before. Before the cameras were on the phones, we had, remember those, what were they, VCR cameras, camcorders that people would have on their shoulders, and post those to all manner of pre-web and now the web. So now that we have this incredible amount of visual data in the world, in servers, stored in data centers globally, now we have a lot of visual content needed to train computer vision, and training is crucial. So, how does computer vision work? Well, computer vision has four basic components. The first is what you call image acquisition, and this mirrors how we see. We have image acquisition where the system captures visual data using cameras, sensors, various scanning technologies, very much similar to how our eyes take in light. Next comes image processing, where the raw visual information is enhanced and cleaned up to improve quality and clarity, very much like our brain acting as a filter to take in the visual signals that it's trying to focus on. Then we get to feature extraction, which identifies key patterns, edges, distinctive elements within images, very similar to how we notice defining characteristics of objects. And finally, and most important, well, I guess they're all important, but at the top of this core components process, image understanding, to interpret what objects are present, how those objects relate to each other, just as our brain can make sense of a complete scene by understanding not just what we see, but the meaning of what we see. And that is very, very important. Now, the techniques that make up computer vision, there are four of them. You have the object detection and recognition, which is like an eagle spotting the prey, and then it has to identify and classify those specific objects within the image, like the eagle knowing that that's a rat or that's a rabbit, as opposed to something a lot larger that it shouldn't attack. Then you have the image segmentation that divides the images into meaningful parts for detailed analysis, much like how we might focus on different elements of a scene. Motion analysis is the next step in the process. This tracks movements across video frames, essential for applications like traffic monitoring, for example. Now, if you think about it, and we all do this, motion analysis, but when the eagle is swooping in to get that rat a quarter of a mile away, the rat's probably going across some underbrush, and the eagle has to adjust, and get it right where it is. Now, of course, we all make those adjustments. A wide variety of creatures in the animal kingdom can make those adjustments, but the eagle does it at a remarkable distance, always, always, always adjusting its path. And that's what computer vision does. It's tracking the movement so it can adjust its approach as in an autonomous vehicle. And then finally, you have the 3D vision, the last core component, key technique, of computer vision. 3D vision represents an extraordinary frontier of understanding the depth and three-dimensional structure of visual data, even if it's in a two-dimensional format. This allows computers to comprehend the physical world in ways very similar to how our eyes perceive the physical world, gives us depth perception. All of these techniques work together, and they build on the others to create a very, very sophisticated model of computer vision. So oh, come on, don't be shy. There we go. So what are some of the real world applications already taking place. Computer vision is obviously used in autonomous vehicles. It serves as the car's eyes, providing crucial depth perception. An 18-wheeler on the highway, it has to know where all the cars, the other vehicles are around it, what lane it's in, when to shift lanes, when to slow down, when to speed up. All of that wouldn't be possible without computer vision. And that's actually obviously a huge, huge step in public safety. Medical imaging applications help healthcare professionals spot diseases in x-rays, MRIs, and CAT scans, sometimes catching details that the human eye might miss. And that's because we can train these systems on millions and millions of x-rays or millions of MRIs, far, far more than any doctor could see in the course of even a long career. So by training these computer vision models on massive amounts of data, it can pick up those tiny details that even the most practiced physician might meet. This has the enormous potential to identify disease far earlier in their development in the body, which means treatment can be started a lot earlier. Now, it's not anyone's intention to use computer vision to replace medical professionals, but this is like an extra tool that enhances their capabilities, similar to how eagles use their exceptional vision to spot things that would be invisible to other birds. The impact on the transportation, freight forwarding, logistics industry, and healthcare outcomes for medical professionals, which ultimately benefits us, the patient. This shows how computer vision creates value far beyond thinking, hey, this is just a cool technology. But the applications, the real world applications, don't stop there. We're naming two others, but there's more than four. But two more that we'll talk about here. Facial recognition technology. This is huge in security systems, authentication processes, really no different than when your phone's face scans you and scans your face, and says, yep, that's you. It'll open up the phone. That's a type of a computer vision technology. And of course, we see this more and more now at airports and other secure facilities like lock rooms and safe rooms and so on. In the manufacturing world, and this is especially interesting, it's one of those dull things we don't think about, but it's hugely important. Computer vision can handle quality control and defect detection, examining products at speeds and precision that we, the people, can't possibly match. Industrial inspection systems can spot the most microscopic flaws in everything from microchips to car parts, maintaining a level of quality while keeping costs down. It never gets tired. You see, an individual who has to look at thousands of parts in an 8-hour period, their eyesight might get tired. They might get bored. It's tedious work. Well, a computer vision is going to excel at repetitive visual tasks that would be tedious or very close to impossible for humans to do. This not only frees us up to do more complex, more creative work, but also ensures that only quality parts, quality systems are processing through a manufacturing plant. This has enormous cost savings over time. Now, there are very key advantages to computer vision because it complements, even exceeds our own human visual capacity. As we just talked about, it's excellent for the automation of repetitive visual tasks. It means computers can analyze thousands of images, as we said, without getting tired or bored. Same level of attention from the first image to the thousandth or 10,000ths. This allows for data-driven insights. It allows systems to extract quantifiable information from visual scenes, giving us insights that we might not have been aware of otherwise. This becomes what they call actionable data, all because it can take in at enormous speeds, enormous quantities of information that we simply couldn't do. But once we have the information, it identifies the patterns with other AI tools, and we realize, oh, this is what's going on in our facility that we may not have known about, and now they can address. So it comes down to enhanced perception, and that means systems like computer vision can see beyond the visual limitations, detecting infrared light analyzing microscopic details, processing satellite imagery. Consistent monitoring provides tireless observation without fatigue, perfect for security applications, long-term visual analysis. Um, this is going to become a computer vision will become a common complement to our own human vision and understanding our ability to comprehend the visual world around us. But like all technologies, excuse me, sorry about that. Like all technologies, computer vision has challenges. It has limitations. Um, a big one is what we call visual ambiguity. We have the incredible ability to infer what we see when we don't have a clear line of sight to something. So, an unusual perspective, lighting conditions, an obscured view. In other words, you're looking at a home, but there's something blocking the home. Well, computer vision still struggles to say, well, that's a house. We know there's a house back there, even though there's something blocking it. So that's called the visual ambiguity, or as we just said, obscured views. We handle these things easily, and we do it by the age of, 2 or 3. I mean, we're incredibly smart this way. But computer vision still struggles with this sort of thing. And then there's what we call contextual understanding. This is an ongoing challenge. You can train computer vision in very specific environments, maybe like security in a warehouse, but the, but if you start to give it complex scenes outside of what it's been trained on, it really struggles with that. As more and more visual data goes into computer systems, that'll probably decrease. Excuse me. But today, it's still very much one of the challenges, whereas we do it very, very easily. The other issue with computer vision, and this is true pretty much of all the AI technologies, high computational needs. It needs sophisticated systems to train. Those require a lot of power. This doesn't get talked about a lot, but in many ways, artificial intelligence technologies, any of them, they're not really green technologies. They need massive amounts of computing power. And that's all the truer for what we call real-time analysis. Think, an eagle's brain is about this big. It just does it. But we need massive servers massive numbers of servers in data centers all over the world. And then, of course, there's the ethics. And ethical concerns are at the core of every AI level of the pyramid around privacy, about misuse of the surveillance technologies, the ability to take computer vision and manipulate it and put it out and say, well, this is what the computer saw when it wasn't. It's deliberate misinformation. So these limitations, these challenges, they have to be worked out because computer vision is only going to become more and more common in society. Generations after mine, the younger generations, they're going to grow up with this technology and how their lives interact with it. That's something we really need to be thinking about. But where does that bring us to? Well, even with those challenges, those limitations, this eagle is going to keep soaring. There are very exciting trends on the horizon. What we call multimodal integration will combine computer vision systems with other sensory inputs like sound and even touch. This creates a more comprehensive understanding, similar to how we use multiple senses. I'm sitting here at this desk. I not only see the desk, I can touch it. So that's more and more information. For better or for worse, this is where all AI technologies are going to go, learning to pull in more and more information of the world around it. And computer vision is a core part of that evolution, if you will. Now, there's a term called few-shot learning. And few-shot learning means systems will require fewer and fewer examples to learn new objects. That is well along in its trajectory. And this is how this mimics how we as human beings can see something just once or twice, and then we've got it. We know what it is after that. And then there's edge computing, which moves computer vision from mostly cloud applications into local devices like your phone. So that'll allow for faster response times and greater privacy. Maybe not as much of us will be out in the cloud. And then finally, what we call advanced scene understanding will help systems comprehend complex visual narratives and situations. So this this computer vision eagle, it's going to keep soaring. It'll open up new possibilities in healthcare, in manufacturing, probably in entertainment. There are people right now saying, hey, how far can we push this envelope? And at the end of the day, this is going to enhance and be fully integrated with how we see the world with our vision. So, so that's our module on computer vision. We hope you enjoyed it. My name is Jack Heslin. I'm the founder of the online community, The AI Conversation, where people from all backgrounds and all levels of interest in AI can come together, learn about AI tools, share how we use them, what works, what doesn't work, so we all learn the best ways, the most practical ways to use this absolutely extraordinary technology. Check us out at www.theaiconversation.com. Thanks very much, and we'll see you in the next module, AI Robotics. Stay well.